Control theory, a branch of control engineering and applied mathematics, focuses on managing dynamical systems. The main goal is to create a model or algorithm that dictates how system inputs should be applied to guide the system to a desired state, minimizing delays, overshoot, and steady-state error. This aims to ensure stability and often aims for an optimal outcome. A vital component in achieving this is employing a controller with the necessary corrective behavior. This controller oversees the process variable being controlled and compares it with the reference or set point. The disparity between the actual and desired process variable value, known as the error signal, or SPPV error, is leveraged as feedback to initiate a control action that aligns the process variable with the set point. Additionally, aspects like controllability and observability are also explored within this field. The applications of control theory are vast, impacting industries such as manufacturing, aviation, and communications, and catalyzing the emergence of fields like robotics. A common method employed in control theory is the block diagram representation, utilizing the transfer function, system function, or network function to mathematically model the relationship between input and output, structured on the system's differential equations. Control theory has roots dating back to the 19th century, with James Clerk Maxwell laying the theoretical groundwork for governor operation. Further progress in the field was propelled by Edward Ruth, Charles Sturm, Adolf Hurwitz, and Nicholas Minorski, who collectively contributed to establishing control stability criteria and advancing PID control theory. Beyond its traditional application in control systems engineering for robotics and industry, control theory finds utility in both natural and behavioral sciences. Serving as a fundamental theory for feedback systems, control theory is applicable wherever feedback mechanisms exist, extending its relevance to domains like economics, operations research, and the life sciences. Control systems have a rich history dating back centuries, with formal analysis gaining traction due to physicist James Clerk Maxwell's work on the centrifugal governor in 1868. Maxwell's study unveiled the concept of self-oscillation, demonstrating how delays in the system could trigger overcompensation and instability. This revelation spurred significant interest, leading Maxwell's classmate Edward John Ruth to extend these findings to a broader range of linear systems. Concurrently, Adolf Hurwitz delved into system stability using differential equations in 1877, resulting in the now famous Ruth-Hurwitz theorem. Noteworthy advancements in dynamic control emerged in crewed flight, notably with the Wright brothers' successful test flights in 1903. Their ability to maintain control during sustained flights was crucial for aviation progress. Control theory gained further prominence during World War II, with Irmgard Fluge-Lotz pioneering the theory of discontinuous automatic control systems, particularly in developing automatic flight control equipment for aircraft using the bang-bang principle. Beyond aviation, discontinuous controls found applications in fire control systems, guidance systems, and electronics. Mechanical methods like ship stabilizers, which counteract roll in ships, have also been employed for stability enhancement. Modern ship stabilizers are gyroscopically controlled active fins adept at adjusting their angle of attack to counter external forces. In the space race, precise spacecraft control was paramount, underscoring the importance of control theory in various fields, including economics and artificial intelligence. In economics, accurate trading models that mirror market dynamics enable better market control and profitability extraction. Two fundamental types of control loops are present: open-loop control, feed-forward, and closed-loop control, feedback. In open-loop control, the controller's action operates independently of the process output, or controlled process variable. An illustration of this is a central heating boiler, regulated solely by a timer, providing heat for a fixed duration, regardless of the building's temperature. Although the control action involves switching the boiler on or off, the controlled variable ideally should be the building temperature, which is not the case in open-loop control. Closed-loop control, on the other hand, ties the controller's action to the process output. In a scenario akin to the boiler analogy, this setup incorporates a thermostat observing the building temperature to relay a signal back, ensuring the controller maintains the building at the temperature specified on the thermostat. Thus, a closed-loop controller operates with a feedback loop, guaranteeing that the controller adjusts its action to align the process output with the reference input, or set point. Consequently, closed-loop controllers are also known as feedback controllers. According to the British Standards Institution, a closed-loop control system is defined as a control system equipped with monitoring feedback, where the deviation signal resulting from this feedback is utilized to regulate the final control element's action to minimize the deviation to zero. And similarly, a feedback control system is described as a system that strives to uphold a defined relationship between one system variable and another by comparing functions of these variables and utilizing the disparity for control purposes. A closed-loop controller, also known as a feedback controller, utilizes feedback in its control loop, unlike an open-loop controller. In a closed-loop system, feedback is employed to regulate the states or outputs of a dynamical system. This feedback loop involves the process inputs affecting the process outputs, which are then measured by sensors, processed by the controller, and fed back as an input to the process, effectively closing the loop. In linear feedback systems, a control loop consisting of sensors, control algorithms, and actuators is structured to maintain a variable at a specific set point, SP. An illustration of this concept can be seen in the cruise control of a vehicle, where external factors like hills can impact speed, and the driver can adjust the desired set speed accordingly. Through the PID algorithm within the controller, the actual speed is adjusted to the desired speed efficiently, minimizing delays or overshoots by regulating the engine power output. Closed-loop controllers offer several advantages over open-loop controllers, including disturbance rejection, assured performance even in the presence of model uncertainties, stabilization of unstable processes, decreased sensitivity to parameter variations, improved reference tracking, and better rectification of random fluctuations. In some systems, both closed-loop and open-loop controls are employed simultaneously, with the open-loop control termed as feed-forward, enhancing reference tracking performance. One of the common architectures for a closed-loop controller is the PID controller. Control theory branches into linear and nonlinear categories. Linear control theory deals with systems following the superposition principle, where the output is proportional to the input, regulated by linear differential equations. Linear time invariant, LTI systems, a significant subgroup, possess fixed parameters and are analyzable through techniques like Laplace, Fourier, Z-transforms, Bode plot, root locus, and Nyquist stability criterion. These methods allow for the delineation of a system in terms of bandwidth, frequency response, eigenvalues, gain, resonant frequencies, zeros, and poles, providing solutions for system response and design strategies for most systems. On the other hand, nonlinear control theory pertains to systems deviating from the superposition principle, capturing a broader range of real-world systems due to their inherent nonlinear behavior governed by nonlinear differential equations. Mathematical tools for nonlinear systems are more intricate and less versatile, restricted to specific system categories. Techniques like limit cycle theory, Poincare maps, Lyapunov stability theorem, and describing functions offer insight into nonlinear system behavior. When analyzing nonlinear systems, numerical methods are commonly employed, such as simulation in a computational environment, to approximate system dynamics. Linearization through perturbation theory enables the application of linear techniques for solutions near stable points in nonlinear systems. Mathematical techniques for analyzing and designing control systems are divided into two main categories: frequency domain and time domain state space representation. In the frequency domain, state variables and system functions are expressed as functions of frequency through tools like the Fourier transform, Laplace transform, or Z-transform. This transformation simplifies the mathematics involved, converting differential equations into easier-to-solve algebraic equations in the frequency domain. However, this method is limited to linear systems. On the other hand, time domain state space representation portrays the state variables in terms of time, describing the system with one or more differential equations. This approach is commonly used for analyzing real-world nonlinear systems which cannot be handled using frequency domain techniques due to their linearity constraints. While solving time domain models can be more complex, the advent of modern computer simulation techniques has made their analysis more manageable through tools like simulation languages. Modern control theory favors the time domain state space representation over the classical frequency domain analysis, using a mathematical model that relates input, output, and state variables through first-order differential equations. By encapsulating the system's dynamics in a set of equations, the state space representation treats all variables as vectors and organizes differential and algebraic equations in matrix form, a feasible task only for linear dynamical systems. This method enables a concise and effective way to model and analyze systems with multiple inputs and outputs, offering a more streamlined alternative to encoding system information through Laplace transforms as required in the frequency domain technique. Unlike frequency domain analysis, the state space representation can handle nonlinear components and non-zero initial conditions, providing a flexible framework for system analysis and design where the state variables define the system state in a multidimensional space. Control systems can be categorized based on the number of inputs and outputs they encompass. Single input, single output SSO systems are the most straightforward, with one control signal regulating one output. Examples include a cruise control mechanism and audio systems, where the input audio signal influences the sound waves emitted from the speaker. On the other hand, multiple input, multiple output MIMO systems are more intricate, as seen in modern large telescopes like the Keck and MMT. These telescopes have mirrors with numerous segments controlled by actuators. A MIMO control system adjusts the mirror's shape using data from multiple sensors to counterbalance changes caused by factors like thermal expansion, stresses from rotation, and atmospheric turbulence affecting the wavefront. Complex systems like nuclear reactors and human cells are often simulated as large MIMO control systems on computers for analysis purposes. Classical control theory mainly focuses on single input and single output, CSO, system design, except when examining disturbance rejection with a second input. Analysis in this theory is conducted in the time domain using differential equations, the complex S domain with Laplace transforms, or the frequency domain by transforming from the complex S domain. Many systems are assumed to exhibit a second-order single-variable system response in the time domain. Controllers designed through classical theory often necessitate on-site fine-tuning due to potential inaccuracies in design approximations. Despite this, due to the simpler physical implementation compared to modern control theory, classic controllers, such as PID controllers, remain prevalent in various industrial applications. These controllers may occasionally incorporate lead or lag filters. The primary objective remains meeting predefined requirements in the time domain, focusing on the step response, or sometimes in the frequency domain, examining the open-loop response. Specifications often include characteristics like percent overshoot, settling time for step response, and gain and phase margin alongside bandwidth for open-loop response. In contrast, modern control theory adopts a state space approach to tackle multiple input and multiple output MIMO systems, surmounting the limitations of classical control theory in more advanced scenarios, such as fighter aircraft control. However, the trade-off involves the inability to conduct frequency domain analysis. In modern design practices, systems are ideally modeled as a series of decoupled first-order differential equations utilizing state variables. This methodology accommodates nonlinear, multivariable, adaptive, and robust control theories. The relatively recent emergence of modern control theory leaves many unexplored areas, with prominent scholars like Rudolf E. Kalman and Alexander Lyapunov shaping its development. The stability of a general dynamical system with no input can be analyzed using Lyapunov stability criteria. For systems with input, stability is determined by input-to-state stability, ISS, a combination of Lyapunov stability and a concept akin to bounded input, bounded output, BIBO, stability for linear systems, ensuring the output remains bounded for any bounded input. Specifically looking at continuous time and discrete time linear systems, stability is attained when all poles of the transfer function have negative real values. In continuous time, this means the complex poles must reside in the open left half of the complex plane when using Laplace transforms. Conversely, in discrete time, the poles should be inside the unit circle when employing the Z-transform. Asymptotic stability is achieved when these conditions are met, resulting in system variables consistently decreasing from their initial state without persistent oscillations. Permanent oscillations manifest when poles have zero real parts, continuous time, or a modulus of one, discrete time. Marginally stable systems exhibit responses that neither decay nor grow over time, with no oscillations, characterized by non-repeated poles at the origin of the complex plane, real and complex components being zero. Oscillations arise when poles with zero real parts possess non-zero imaginary parts. Analysis tools like root locus, Bode plots, or Nyquist plots are commonly used to assess system poles. Enhancing stability is crucial, with mechanical adjustments such as adding ballast to ships or incorporating anti-roll fins on cruise ships to mitigate rolling. Controllability and observability play crucial roles in the preliminary analysis of a system to determine the most suitable control approach and its feasibility in stabilizing the system. Controllability concerns the system's ability to be driven to a specific state using an appropriate control input, implying that if a state is uncontrollable, no input will influence it. However, if an uncontrollable state features stable dynamics, it can be termed as stabilizable. On the other hand, observability deals with the system's state being deducible through output observations. An unobservable state makes it impossible for the controller to understand its behavior and consequently stabilize the system. Despite being unobservable, a state may still be detectable. Geometrically, for a system's variables, all undesirable states must be both controllable and observable to ensure favorable performance in the closed-loop system. Failure to meet this criterion means that any uncontrollable and unobservable eigenvalues will persist in the closed-loop system, potentially rendering it unstable. Unobservable poles are absent in the transfer function form of a state space model, which is why it is sometimes preferred in dynamic systems analysis. Remedies for issues in uncontrollable or unobservable systems involve integrating actuators and sensors. Various control strategies have emerged, ranging from general ones such as PID controllers to specialized approaches for specific system classes like robotics or aircraft cruise control. Stability is a core requirement in control, where the controller must maintain closed-loop system stability regardless of open-loop conditions. Ill-advised controller selection can exacerbate open-loop stability concerns and should be avoided. Desired closed-loop dynamics, disturbance rejection, and performance metrics regarding time response and frequency domains are typical control specifications. These specifications govern factors like rise time, peak overshoot, settling time, and robustness, among others. Contemporary evaluation methods often utilize integrated tracking error variance for performance assessment. Ensuring model identification and robustness in a control system is crucial for its operation. A robust controller maintains its properties even when dealing with a system slightly different from the one it was initially designed for. This is significant because real-world systems do not precisely adhere to the mathematical models used to represent them. Often, a simpler model is adopted for ease of computation, considering that accurately modeling the complex dynamics of a system can be challenging. System identification plays a key role in determining the equations governing a model's behavior. This process involves deriving an approximation of the mathematical model, typically in the form of a transfer function or matrix, based on a series of measurements. However, this approach may overlook unobservable dynamics. Alternatively, models can be constructed based on known physical equations, such as in the case of a mass spring damper system. Even when a complete model is utilized to design the controller, the nominal parameters within the equations are not precisely known. Control systems must adapt to variations in parameter values when connected to physical systems. Advanced control techniques incorporate online identification processes to calculate model parameters while the controller is operational. This real-time adjustment ensures proper system performance, especially when facing significant parameter changes, like a sudden release of weight by a robotic arm. In analyzing the robustness of a single input, single output (SI-SO) control system, frequency domain techniques are employed, with considerations given to the system's transfer function using tools like Nyquist and Bode diagrams. For more complex systems like multi-input, multi-output (MIMO), specific control techniques must be tailored to meet the desired robustness qualities. Understanding gain and phase margin as well as amplitude margin is essential in evaluating system robustness. Addressing input and state constraints is a critical aspect of ensuring system robustness. Controllers must operate effectively within signal limits to avoid issues like exceeding physical system constraints that could lead to undesired behavior or damage. Techniques like model predictive control and anti-windup systems are utilized to mitigate these challenges, with the latter preventing control signals from surpassing predefined thresholds, thereby maintaining system stability and performance. Pole placement for MIMO systems is achievable through a mathematical approach utilizing a state space representation of the open-loop system, requiring the calculation of a feedback matrix to assign poles at desired positions. In intricate systems, this procedure may necessitate computational assistance and may not always guarantee robustness. Additionally, since not all system states are typically measured, the integration of observers becomes crucial in the design of pole placement. In the realm of nonlinear control, industries such as robotics and aerospace often face significant nonlinear dynamics challenges. While linear techniques can sometimes be applied after linearizing these systems, developing theories from the ground up may be essential for effective control in many scenarios. Techniques such as feedback linearization, backstepping, sliding mode control, and trajectory linearization control rely on results rooted in Lyapunov's theory to tackle the complexities of nonlinear control. Differential geometry plays a crucial role in extending established linear control concepts to nonlinear systems, highlighting the intricacies that make nonlinear control a more intricate problem. Control theory's applications extend to understanding the neural mechanisms that govern cognitive states. Decentralized control systems come into play when a system is overseen by multiple controllers. Decentralization offers advantages such as enabling control systems to function over vast geographical regions. Agents within decentralized control systems can communicate through channels and coordinate their activities effectively. Stochastic control involves state variable evolution influenced by random external shocks, whereas deterministic control problems do not involve such random external interferences. In the realm of control systems, ensuring the stability of the closed-loop behavior is of paramount importance. Linear systems achieve stability by placing the poles, while nonlinear systems rely on theories like Alexander Lyapunov's theory. Different control techniques cater to various needs and specifications depending on the model and chosen control strategy. Optimal control focuses on optimizing a cost index, such as minimizing fuel consumption in satellite trajectory adjustments. The widely utilized methods for optimal control design are model predictive control, MPC, and linear quadratic Gaussian control, LQG, which guarantee closed-loop stability. MPC stands out for its ability to consider constraints on system signals explicitly, making it crucial for industrial processes. Robust control addresses uncertainty in controller design, ensuring performance despite small discrepancies between the actual system and the model. Notable robust control techniques include H-infinity loop shaping, sliding mode control, SMC, and protocols for managing electric loads in smart power grid applications. Stochastic control tackles design under model uncertainty, accounting for random noise and disturbances. Adaptive control, with applications dating back to the 1950s in aerospace, relies on real-time parameter identification or controller gain adjustments for robustness. Hierarchical control structures devices in a tree-like arrangement with governing software, particularly effective when networked. Intelligent control leverages AI techniques like neural networks, fuzzy logic, and machine learning for dynamic system management. Self-organized criticality control intervenes in dissipating energy within self-organizing systems to influence processes.